Hi, how's it going? So I figured I would do a little bit of a math review. What I'd really like to do is jump in and look at some functional analysis. However, before I do that, I'm just going to go back and look at topology. This video series, we're going to start with topology, then we're going to work on to functional analysis. For this series, if you'd like to follow along, I'm just using the standard Dover math book on topology. It's pretty good. And yeah, I'll be sort of doing little reviews on bits of it. So to start with, we have topology, and topology, a topological space is a set and some sort of structure. Like it could be a function or a relation which puts some constraints on a system and makes it behave a certain way. And we can actually generalize a lot of mathematical structures as topological spaces. But the purpose today is to look at sets. I know it's going to be pretty basic, but we'll do what we can. So some examples of sets. A set is a mathematical structure which has a collection of elements. And the elements can pretty much be whatever we want them to be. Here's a set A. It has the elements are 1, 2, and 3. Sets can contain sets. So here's a set B. As its first element, it will be the set with 1 and 2. And then, who knows, 5. Okay, fair enough. If we want to say that something is an element of a set, then we do it with this sort of symbol here. People used to tell me, hey, this looks a little bit like an E, like element. And that kind of messed me up because I was like, well, it doesn't look like an E. It looks like a euro or something. But this is the symbol for it. And the way we read this, we would say 1 is in A. We have it. If something is not an element, then we get that euro and we strike it through. So this is 4 is not in A. 4 is not an element of A. It's possible to say, okay, A, and it doesn't matter what A is. A could be this thing up here, A could be something else, will always be an element of the set containing that thing. But the reverse is not true. So to look back at the example above, we have 1, 2, 3, and 1 is in A. But if I were to make a set with 1, that is not in A. Whereas the set with 1 and 2 is an element of B, as we can see there. Hopefully that sort of makes sense. Another really important thing is the empty set. So the empty set is just a set of braces, and we call that phi. There we have it. As the null set, we call it that. Now, it turns out, if you're really mischievous, you can define your whole math system based on empty sets, but we're not going to do that. So, okay, we have that. Then we have the definition of a subset. So we say, if some element being in a set A guarantees that that element will be in a set B, then we say that A is a subset of B. The reverse need not be true. Okay, so if I have a really contrived example, 1, 2, and then my set B is 1, 2, 3. Yeah, everything in A is in B, but there exists something in B which is not in A. Okay. Another way to say this, another way to rephrase this is to say, if for all elements in A, that element is in B, then A is a subset of B. Okay, now I said that the opposite need not hold. However, if the opposite holds, then the sets are equal. So we say the set A is equal to the set B if and only if A is a subset of B and B is a subset of A. Okay, so everything that's in A is in B, and if I can show that everything in B is also in A, then those sets are equal. In other words, all of the elements are the same. Elements in a set don't need to be ordered. They can just be, you know, if I have the set which is 5, then the set with 1, 2, in this B but reordered, those are both equal to each other. Okay, so, oh yeah, this is super important. In future, if I'm ever proving that two sets are equal, I will attack it this way, because this sort of approach is not going to work. It's not good. Whereas this is something more concrete that I can show. Because often when I'm trying to prove something, I'll just have abstract sets, and I'll just know something about their properties, not about what the actual sets are. Still speaking about subsets, doesn't matter what we've got, it's always true that a set will be a subset of itself, and surprisingly, the empty set is a subset of any set. Why do you think that is? Remember the definition for a subset. The definition is something in a set has to guarantee that something is in the other set. Okay, so if we look at what we've got here, we're saying everything in the empty set guarantees that it's in my target set. Well, wait a second. Nothing's in the empty set. So if I were to break this down into true-false, this would be like a false statement guarantees something. And in implications, this is what's called vacuously true. Okay, so the only case where an implication statement fails is if the condition is true and then the result still ends up false. That's bad. However, if the condition is false, then we actually don't care what the result is because the guarantee still holds. This is vacuously true. So for that reason, the empty set is a subset of everything. Okay. Now these examples are what we call improper subsets. But I wouldn't worry too much about that. The whole improper subset, proper subset thing, it's not too hard to remember, and it doesn't really show up a lot in mathematical statements. We're usually worrying about bigger picture things. Okay, so there's that statement there. Another important thing to think about is intervals. This is an example of sets. So if I have a set which is 1, 2, 3, then this is a finite set. It has size 3. If I have a set which is the natural numbers, so 1, 2, continuing, it is countably infinite because it has an unbounded number of elements, but I can still count 1, 2, 3 through them. Real numbers are uncountably infinite. They're represented in different ways. So let's say we have the real number line. So this is all the real numbers. And we consider 2 points on the real number line. Then we can have common interval notation, A to B. Now these dots with the equal, that means I'm defining it to be this thing. So this is what it is, and it's going to be defined this way. This is what we call set builder notation. There's 2 parts. There's a stroke, and on the left-hand side is a description of the general element. So it's going to hold real numbers. And then on the right-hand side, there's the condition that the real number has to satisfy, the element has to satisfy. And in this case, it is that x is bigger than or equal to a, less than or equal to b. That is interval notation. If I were to draw this, of course, be filled in dots and line between them. Okay. On the other hand, these endpoints can have any combination we want, open or closed. This is the open interval. It's defined to be the set of real numbers with the condition that the real number is bigger than or less than the bounds. And like I said, we can have any combo, so we can be open on one end, closed on the other. That's fine. The way we draw this is we'd have open points because we're excluding a and b, and then everything in between. So we have, it's a statement that the open interval is a subset of the closed interval, which is a subset of all the real numbers. Okay, so pretty obvious, but does the reverse hold? No, and we don't need to do too much work in showing this. All we need is a counterexample. Okay, so for this closed interval to be a subset of the open interval, then it needs to be for every point in the closed interval, that point is in the open interval. Well, if x equals a, that's in the closed interval, but not in the open interval. So the reverse does not hold. Similarly, if I go a minus 1, that's in the real numbers. It's not in the closed interval. So this subset does not reverse. So these sets are not equal to each other, but they are subsets. Okay. The last thing I want to note is the power set of a set. So the power set of a set is, it's a set of sets with the condition that each element, each set, is a subset of A. So for countably, like for finite sets, this is easy enough to show. Let's look at A. Okay, so the power set of A, again, sets don't have to have an order, but I will use an order here just to organize my thoughts. I think, okay, what are all the subsets of A which have 0 elements? That's just the empty set. Okay, what are all the subsets which have 1 element? Okay, what are all the subsets which have 2 elements? Okay, what are all the subsets which have 3 elements? Okay, cool. So there we have it. As a side note, if you have a finite set and you take its power set, then that will have 2 to the n elements. So if this thing has 3 elements, then its power set has 2 to the 3, which is 8. So as we can see here, we have 1, 2, 3, 4, 5, 6, 7, 8 elements. We can also see, yes, the empty set is a subset of A. The original set is a subset of A. And there we have it. So this has just been a quick sort of review of some basic set theory.